Alright, so that last video was long. Hopefully I did the right thing and split that up into multiple ed puzzles for you so you don't have to do a 34-minute ed puzzle. So if you see multiple ones, that's why, because, oh boy. But luckily, a lot of that we just unpacked is going to apply to here, so this one will hopefully be able to be shorter. The main point that we left off with, that I really wanted you to stick from the last video, was about how sound waves travel at different speeds in different media. And really that kind of applies to pretty much all mechanical waves. And the idea is that with mechanical waves, since they are the medium, the energy has to transfer from molecule to molecule to molecule to molecule, right down the line. So the closer the molecules are together, the faster the signal can get there. The more spread apart they are, the longer it takes for the signal to get to the other side. Now, electromagnetic waves are different, right? They're not the medium. They're kind of this weird own medium thing, right? Or they're just like the electric fields and the magnetic fields kind of like oscillating like this as they go that way. So they're kind of oscillating at perpendicular angles as the energy goes in the the third direction there. Right? If magnetic field is in X, electric field is in Y, well then the energy is going to be sent in the Z direction. Right, so this is kind of the right-hand rule that we talk about. So you got like the X direction, the Y direction, and the Z direction is the direction the energy actually travels in. And that energy kind of travels through the medium. Now that's a way oversimplification of it. But the best way to think about it conceptually is that it has to kind of push the medium out of the way, or kind of steer around the molecules there. And that means you're going to see here kind of in a second, like the opposite rule applies for electromagnetic waves. So let's check this out.
We all know that light bends when it travels through glass, water, or other transparent material.
We'll get to that in the next video.
That's how a microscope, lighthouse, and spectacles all work. And you might even know that light bends because it travels slower through glass or water than through air.
So that's called refraction. We'll talk a little bit more about that later. But the bending of light due to the bending of any wave due to its change in speed is called refraction, and that's going to be very important in a minute.
But why does light slow down? And how does it speed up again when it comes out on the other side? There's nothing there to give it a push. Well, if you think light is a wave, it's easy to explain. Electromagnetic waves simply travel slower through glass than through air. So the wave crests are closer to each other, but the light still oscillates the same number of times per second. It stays the same color. When the wave hits the air again, its color still doesn't change, while the crests spread out and it returns to light speed. The simplified explanation is that the energy of a wave is determined by its frequency or color, which doesn't change. So it doesn't need a boost to speed up at the other side. But wait, you say, I thought light traveled at the same speed in every reference frame. You still haven't explained how it can slow down.
So that's a big thing. Like a huge positive special relativity and everything like that Einstein came up with is that light travels at the same speed in all reference frames. Yes, but also, in the same medium. So all electromagnetic waves will travel at the same speed when they're in the same medium. So when they're in that medium, they'll all be traveling at the same speed regardless of the reference frame you're looking at it from. Look way more into that. Like, search special relativity on YouTube if you want to go down that rabbit hole. It's a lot of fun. Come to a Zoom session. We'll talk about it sometime.
Well, now let's think about light as a particle. When light goes through glass, it gets knocked around and bumps into all sorts of molecules and electrons. So whenever it's traveling at the speed of light. But it's busy interacting with and scattering off lots of stuff along the way.
And this is kind of how you have to think about it, right? So when electromagnetic waves are traveling through a more dense material, or something with a higher index of refraction, as they refer to it, because it's not exactly density, it's more like how they interact with the particles, but for us, we can think of it as density. They kind of have to steer out of the way of more molecules. So they're just taking a longer path. They're still traveling at 3 times 10 to the 8th. It's just that through air, they can take a straight line path, so it doesn't take as much time. Whereas through more dense materials, they kind of have to bob and weave a little bit, and that way they can kind of appear to be taking less time or appear to be slowing down, even though they're really traveling at the same speed throughout the whole thing.
And it doesn't necessarily take the shortest path through the glass. It's like the President of the United States trying to cross a room. If the room is empty, he can walk across directly. But if the room is full of people, all of whom want to shake the president's hand, even though he walks from person to person at full presidential speed, he'll get slowed down along the way. As soon as he reaches the far side of the room, though, he's free to resume his pace. Full speed ahead, Mr. President.
Yeah. So, or any politician, whatever. When you're walking through, you're gonna have to move through people. So you're still moving at a pretty fast speed, but your velocity isn't going to be as much because you're not in that direction, because you're not displacing as much in the same amount of time. So that's how we want to think about light. And that allows us to then fill out the rest of this chart that we've been working on here. So we saw with in the last video, mechanical waves travel fastest when the molecules are closer together, and slowest when they're further apart, because the energy has to move from molecule to molecule. And when they're closer together, you can go quickly from molecule to molecule. But when you're spread further apart, it takes more time. But the opposite is true here for electromagnetic waves. Since they kind of have to navigate around the material as they interact with it, they actually move slowest through a solid when the molecules are most closely together, because then they're going to be having to navigate around and interact with more molecules. So as the material gets further apart, they can move faster, which is why they move fastest through a vacuum, because there's nothing in their way. They can just straight through, light speed ahead, cool sci-fi. But again, it's not just the density of the particles, it's also the types of particles that they interact with. That's more of it has to do with the index of refraction, and it just kind of has to do with like what the chemicals they're made out of, what atoms and molecules the bonds are like, and how they interact with electromagnetic waves. That'll slow down light waves more than others. But
when a beam of light hits a piece of glass straight on, it passes right through it. But the waves that make up the light actually get slowed down by the glass and only go back to their normal speed when they come out the other side. That's slowing down.
Okay, right, so we've already established that. So the light's going to travel slower through this glass here than it is through here.
That slowing down is what causes white light to split into a rainbow of colour whenever it hits glass on an angle.
Pink Floyd, anyone?
It happens because glass slows some colours of light more than others, and because slowing down on an angle makes light bend. It's easy to understand the bending if you picture how the light waves would look from above, like how waves at the beach look if you see them from the air.
So this is actually kind of a confusing explanation here and why we're seeing the bands like this. They do a better job of showing it later in the video like this, right? So like if we look at the waves kind of like this as they travel across the screen, what we're doing is we're actually, each one of those bands is the crests of the electromagnetic wave there, of the energy oscillating forward. So every time you see a long straight line, it's the crests of one. So the closer together they are, the higher frequency wave, and the further apart they are, the lower frequency wave. So we'll go back to that now and let her explain the rest of that.
On an angle. It happens because glass slows some colours of light more than others, and because slowing down on an angle makes light bend. It's easy to understand the bending if you picture how the light waves would look from above, like how waves at the beach look if you see them from the air. And while white light's made up of all the different colours of light...
Right, so this is white light, so we talked about it before when we look at white, but what we're really seeing is a combination of all the visible light that we can see.
It also helps to look at them one colour at a time.
So each one of these is a red wave crest. Red light wave crest. Red light wave crest. Yeah, that's fun to say.
When a wave front of red light hits glass on an angle,
this is
the
important.
part of the wave that enters the glass first gets slowed down before the rest.
So that's the key here. This is why light will bend when it strikes a medium at a different angle. Right? When it went straight on, it was no problem. It just slowed down and then kept going because all of the light wave was being slowed down at the same speed or at the same time. But here, when they're coming in at an angle, part of it is going to slow down first. This part right here with the tip of my finger. So that's going to slow down first while the rest of it kind of curves around. Right? So kind of like... And that's what you're seeing here. We'll pause it. Right, so you can see this part here has been slowed down first. So it's kind of that can't get across the screen as fast, while this one's kind of zooming and catching up, and you get this kind of like almost skidding effect, like a car, like kind of Tokyo drifting, Fast and the Furious.
And that changes the angle of the whole wave, like how waves bend around a cliff. Violet light gets slowed down even more by glass, so its waves bend more.
All right, see, so the purple waves come in even quicker, so they bend even more. since they're coming in even more frequently, they get bent even more as they go. So their path gets disturbed even more than the red light does.
All the other colours get bent somewhere in between. So the colours get separated when they first enter the glass on an angle, and they spread out even more when they speed up on an angle as they leave.
Yeah.
The reason the different colours slow down different amounts in glass is because they've got different wavelengths. Red light has the longest wavelength, followed by orange, yellow, green, blue, indigo, and finally violet with the shortest wavelength. And the shorter the wavelength, the longer it takes to travel through glass.
All right, so you can think of it as every time it oscillates up and down, it's interacting with the material there, which is causing it to slow down. And the violet light is oscillating so much more quicker. It's interacting with it so much more quicker, or navigating around it so much more, right, with each oscillation. It just ends up making it take way longer than the other colors.
That's because light interacts with electrons in the molecules that make up glass. Long wavelength light, like red, only interacts a bit with the electrons, so it doesn't get slowed much. But shorter wavelength violet light interacts more, so it gets slowed down more. So it's the combination of hitting glass on an angle and different wavelengths interacting with the electrons in the glass different amounts that makes light hitting a prism spread out into a beautiful spectrum of colour. And some classic album cover art.
Pink Floyd, Dark Side of the Moon, cool album. So, due to the slowing down of the electromagnetic wave in a different medium, we can get this bending. And this bending and refracting of light is actually kind of the explanation for two of the biggest questions we get in physics. Why are rainbows? And why is the sky blue? Because of this. So check this out.
When white light bounces off the back of a spherical raindrop, the light is spread into colors as if by a prism. You might see red light from one drop, yellow from another, orange from a third, and so on, each part of your rainbow coming from a different raindrop.
Got it? Cool? Alright, moving on. I'm just kidding. Let's go break that down.
When white light bounces off the back of a spherical raindrop, the light is spread into colors as if by a prism.
So, what we're seeing here is the exact same effect that we just saw with the prism. So the white light comes in, and it's coming in at an angle, so it's going to separate out the light, because the waves are going to slow down at different rates. It's going to bounce off the back, and then be shot out this way. And now what happens when it does this is, now if this bending didn't happen, just a straight reflection, then we would just see the white light hitting our eyes. But it would just kind of come straight in, right? And you can see all four of my fingers here, hopefully, maybe. Kind of like combined like this. But because it bends, as it does that, it kind of deflects the angle of some of these waves. And so as it comes towards you now, you can see, now you can only really see my pinky, because the rest of the waves have been diverted away from your eye. So you're only going to see one color from that particular raindrop. Or like a group of raindrops, to be more precise, because if you're looking at them, they're so tiny, you'll probably get more of the beam. But the idea here is that, because the raindrops are different spots, you're going to see different colors being directed towards your eye, which we then can perceive as a rainbow.
You might see red light from one drop, yellow from another, orange from a third, and so on, each part of your rainbow coming from a different raindrop.
I think what I'm going to do is I'm going to take each of these 10-second videos, and I'm going to use that video editing software to slow them down so you can talk really slowly, so we can watch it once real quick and then once real slow. That'd be cool. Not that you need to know that. Let's move on. Also, kind of cool bonus fact here. Any kind of light, like if you had a flashlight out in the dark and you sprayed, like a hose near it, you could still see a rainbow. Also, moonbows are a thing. Like Google image moonbows right now. It's pretty cool because you get off of moonlight, which is still just sunlight, but shh. But when the light's reflecting off the moon, you can kind of see some really cool effects with moonbows. And like we said, this also helps to explain why the sky is blue.
The sky is mainly broad-spectrum white light like the sun, but since small particles in the atmosphere scatter light at the blue end of the rainbow more than the red, it's slightly bluish-white, while the remaining sunlight becomes slightly yellowish.
So, blue-green is actually the most prevalent color in white sunlight. Interesting. So here's what's happening here. So if you're standing looking directly at the sun, typically what you should see is white light coming in, straight at your eyes. But just like the light gets refracted by the water waves, or the water droplets to create a rainbow, the the gases in our atmosphere actually kind of scatter a little bit too. Not nearly as much as the water does, right? Because we know air is easier to move through for electromagnetic waves, but it's still kind of refracted, which is why the sun looks kind of yellowish. Like it's still pretty white, but we typically draw it as yellow because it's got a little bit yellow tint if you stare at the sun. Don't stare at the sun. But when you look at the sky, what you're really seeing, like when you look at my shirt, you're not looking at my shirt. You're looking at the light that's bounced off of my shirt and hit your eyes. So when you're looking at the sky, you're really looking at air particles. And what's happening is that those air particles are reflecting the blue light towards your eyes. So they call this Rayleigh scattering, Rayleigh scattering. Check it out. Search for it on YouTube. There's a whole lot more information about it there. But the idea there is that the same thing is when you look up at the sky, you're really seeing light that's being bounced off of those air particles. And it just bounces the blue light towards your eyes more than any other color, which is kind of cool. So yeah, take a look at that some more. So that's it. This was a much shorter video, or maybe it's a longer video, depending on if I didn't split this up into one or two videos. But each one of these sections should hopefully be a little bit smaller if I did. So what questions or connections do you have now that we've kind of compared and contrast how waves travel in different speeds in different media? That's like a big idea there. And let me know. So hopefully you got a lot of questions because this type of stuff definitely usually comes up with some stuff. But yes, so one of the questions that always comes up is, so if our atmosphere was made of different gas, could the sky look like it would be a different color? Yes, it absolutely could. Don't ask me which gases because I haven't researched that as much, but I'm sure a smarter person than me would be able to explain to you what gases you would particularly need to get the sky to be, I don't know, red or like purple. I don't know. But yeah, let me know what you got, and I will see you in the next video.